So today we will look at in-order predecessor and in-order successor in binary search trees. Specifically, we will be looking at where these are to be found in a binary search tree. In order to understand what an in-order predecessor and an in-order successor are, let us first look at this slightly more general definition. Given a set of integers, or actually any totally ordered set S, stored in a dictionary and an integer x, we define x minus to be the max amongst all those elements in the dictionary which are less than x. The formal definition gives x minus to be the max, so over max of all y in S such that y is less than or equal to x and minus infinity. If x is smaller than all the elements in the dictionary, then we give x minus the default value of minus infinity, and similarly x plus is the largest value, is the smallest value in the set which is larger than x itself, or plus infinity if no such value exists. If S is stored in a binary search tree and if x is in S, then the node containing x minus is called the in-order predecessor of the node containing x, and the node containing x plus is called its in-order successor. The reason for that is that in an in-order traversal of a binary search tree, this x plus would come after x and x minus would come right before x. So here's an example of a binary search tree, and we can see in this particular example that 5 minus, that is the in-order predecessor of 5 is 2 and the in-order successor of 5 is 7. Right, if we take the example of 7, then we see that the in-order predecessor of 7 is 5 and the in-order successor of 7 is 9. That's over here. We see that these are two different cases here. In the case of 5, the in-order predecessor and the in-order successor lie at depths lower, that is, they lie higher up in the tree than 5 itself. In the case of 7, both the in-order predecessor and in-order successor lie at levels which are lower, that is, they lie in subtrees of 7. The case of 13 is interesting in this respect. 13 minus is 12, which lies above 13 in the tree, and 13 plus is 15, which lies below 13 in the tree. So this is also possible. 19 minus is 17, which lies above 19 in the tree, and 19 plus is plus infinity, which does not lie in the tree at all, since 19 is actually the largest element in this set. So now let us look at certain properties of the in-order successor and in-order predecessor, which will help us locate these elements in the tree. So the first property is somewhat obvious. X minus, if x minus is equal to y, then y plus is equal to x whenever x and y are in S. This is fairly obvious, since if y just precedes x, then x just succeeds y in the in-order traversal. Right. Now we come to a somewhat more complex and subtle property, which is very relevant to what we want to talk about. The property goes something like this. If the node containing x has a non-empty left subtree, let us call it Lx, then x minus lies in Lx, and moreover x minus is equal to max y such that y lies in Lx. So what we are saying is that let us consider this x here. Let's consider this node x here, and this node x has a left subtree. We call it Lx, right? We are claiming that x minus lies somewhere in here. X minus is in here somewhere. X minus is to be found in here somewhere, and in fact x minus is the maximum value that lies in this subtree. We're claiming that x minus is in here and nowhere else, to be found nowhere else in the tree. So to prove this, let's try to prove this property. Consider first the path down to x from the root. So there's a path that's coming down from the root towards x, finding x, and let z be the last node where the path turned right. That is, this was a right turn and everything else was a left turn. Everything else was a left turn. So now I have two claims. First claim is that uh, if W is in Lx, then Z is less than equal to W is less than equal to X. That is, any W which lies in Lx lies between Z and X. This claim is quite simple to see because I turned right from Z, therefore all of Lx lies in the right subtree of Z. All of Lx lies in the right subtree of Z, and so every element of Lx is greater than Z. And also by definition Lx is the left subtree of X, and so all of Lx is less than equal to X. So definitely it's very easy to see that W being in Lx implies that W lies between Z and X. Claim 2 is a little bit more subtle. Claim 2 says all other keys, that is all keys which are not in Lx, are either less than equal to Z or greater than equal to X. We will see in a moment how we prove claim 2, but before we do that, let us satisfy ourselves that claim 1 along with claim 2 gives us the result. Note that claim 1 tells us that Lx is less than X, and also that there is this particular node Z which is a witness for the fact that the keys in Lx are the ones which are most immediately below X. Z, by the way, could be minus infinity. There need not be a Z which makes a right turn down on the path towards X. In that case, the only keys that are less than X are those in Lx. But if there is a key which takes a right turn towards X, then claim 2 tells us that that node, the key in that node Z, gives us a lower barrier and says that everything in Lx is above that lower barrier and less than X, which automatically rules out the possibility that either Z itself or all keys which are less than Z are candidates for X minus, and definitely those keys which are greater than X cannot be candidates for X minus, and therefore X minus is to be found only in Lx. So now with this in mind, let us see how claim 2 is proved. So in order to prove claim 2, what we will do is we will start the path down from the root towards X. Here is my X, here is X, and I'm going to start the path from the root down to X. On this path I will encounter or indicate where all the keys in the tree are to be found, or how they are to be characterized vis-a-vis this path. So first let us consider the part of the path which goes from the root down to Z. Now every move in this path is either a left turn or a right turn. So let us consider these separately. So here consider this A. This is an example of a left turn. This is one of the left turns. Now since we make a left turn from A, and noting that X lies below A in a subtree of A, and we are making a left turn at A, that means this implies that A is in fact greater than equal to X, right? Which implies that all these keys in RA, which is the right subtree of A, the one which we are not going to visit, are greater than equal to X. So what we have shown is that when we go on this path, every time we take a left turn, if we consider the subtree that we don't visit, all the keys in the subtree that we don't visit are actually greater than equal to X. We don't need to worry about that. And this node itself, of course, is greater than equal to X. Now consider a right turn. So this is B. From here we turn right to go down towards Z and further X. Now B is less than equal to Z because we took a right turn to go to Z, and so definitely LB is also less than equal to Z. All the elements in LB are less than equal to Z. So if I look at all the keys that do not lie in the subtree rooted at Z, they are of this form. Either they belong to the path or they belong to a subtree that hangs off the path. That subtree is a right subtree if I took a left turn at that node, and is a left subtree if I took a right turn at that node. If it is a right subtree, the keys are greater than or equal to x. If it is a left subtree, then the keys are less than or equal to z. Okay, now let's come into the subtree that belongs to z, and let's head down towards x. First note that this z, from z we know we turned right, because z by definition was the last right turn before we reached x. So from z we turned right. That means z itself, of course, is less than or equal to z by definition, but Lz contains everything less than or equal to z. Lz is the subtree of z we are not going to enter. We are going to enter the right subtree of z in this direction. Now all the nodes that we encounter on the path from z to x, we are taking left turns at each one of them. At each one of them the turn is in the same direction, it's left. So since it is left, if you take any example node, this c is greater than or equal to x, because we are taking a left turn at this c. And definitely if we look at the right subtree of this c, which is the subtree we are not visiting, then since that is greater than or equal to c, which is greater than or equal to x. So now there are only two parts of the tree that we have not actually visited. One is Rx and the other is Lx. Rx is definitely greater than or equal to x by the definition of Rx. It's right subtree. So note now, we have covered the entire tree except Lx, and for each of the subtrees that don't lie on the path, we have characterized it as being either greater than or equal to x or less than or equal to z. The only part which we have not been able to eliminate in this way is Lx itself, which we have already shown to be lying between z and x. So the proof of claim 2 is complete, and we have established that apart from the keys of Lx, all other keys in this subtree which are not z or x are either less than or equal to z, like Lb for a right turn above z, or Lz below z, or are greater than or equal to x, like Ra for a left turn above z, or Rc for a left turn below z above x. So that was the proof of claim 2, and with claim 2 proven, we've proved property 2, which says that if x has a non-empty left subtree, Lx, then x minus lies in Lx, and x minus is the largest value in Lx. So now let us look at the third case, where the third property, which is the second case, that is the node containing x has no left subtree. If the node containing x has no left subtree, then x minus is the key contained in the last node at which the path down to x took a right turn, the z that we were talking about. And we have actually already proved this, because what in claim 2 we showed that only those elements which are in Lx lie between z and x. Only these elements here lie between z and x. And so if x contains no left subtree, then Lx is empty, and so there are no elements which lie between z and x, and hence z is x minus. So claim 3 follows, the property 3 follows from claims 1 and 2 above. So these are the two cases here. If you're looking for x minus, then if x has a left subtree, then we have to go down into the left subtree, find the largest element in the left subtree, which we will do by entering the left subtree with one left turn and then going all the way right. If there is no left subtree, then we have to look at z, which was the point at which the last right turn was taken. Note that symmetric versions of properties 2 and 3 can be shown for x plus. That is, we look at the right subtree of x, Rx. If the right subtree of x exists, then the minimum element in the right subtree gives us x plus. If the right subtree does not exist, then we look at the path down from the root to x, and instead of looking at the last point where a right turn was taken, we now look at the last point where the left turn was taken, and that last point at which the left turn was taken either helps us prove that x plus lies in Rx, or if and helps us show through claim 2, a symmetric version of claim 2, that if Rx is empty, then that point at which the last left turn is taken is in fact x plus itself. Another point to note is that suppose we want to find x minus or x plus for x which are not in S. One way of doing it is to insert or fake insert a dummy node containing x and use property 3 above. Why property 3 and why not property 2? Because whenever we insert a dummy node, whenever we insert any node, whether it's dummy or not, that insertion will happen at leaf level, and so there will be no left subtree or right subtree of the node whose in order predecessor and in order successor we are looking to find.